So now we're back to, again, that same mixture that we started with, where we had 4 molar acetic acid, 3 molar sodium acetate, and now I'm going to add sodium hydroxide in. Again, we talked about how hydroxide is effectively removing an H+. So we know it's going to shift to the right. We've talked about that from a standpoint of Le Chatelier's principle, but now let's talk about it in terms of what it looks like in terms of a reaction. Stoichiometry first. We're going to balance that equation. We're going to find our limiting reactant. We're going to get all the numbers. Then and only then are we going to worry about doing an equilibrium reaction, equilibrium expression. So the first thing, again, this is HC2H3O2, and this is my sodium spectator ions up top, but C2H3O2, the conjugate base acetate ions down below. So now when I add in a base, it's going to react with the acid. So the first thing here is to do the stoichiometry for the reaction. So I'm going to start with HC2H3O2 plus sodium hydroxide, and that's going to make NaC2H3O2, or more specifically acetate ion, because that is aqueous, and water. So we started with 4 moles in a liter container of this. We had 3 of these, and we added in 1 mole per liter of sodium hydroxide. So 1 mole of sodium hydroxide in this liter container is my limiting reactant. It's going to be used up, and therefore it's going to reduce that number of acetic acid moles to 3. On the other hand, this one's going to increase to 4, oh, not plus 4, plus 1, equals 4. So now, after I've done the stoichiometry, and only now, am I ready to go ahead and do my pH calculation and my equilibrium expression. So HC2H3O2, now equilibrium. Again, notice stoichiometry up top first, H plus C2H3O2 minus, where my concentration of acetic acid is 3 molar, no H plus, 4 molar acetate ion, none of this, so I don't have to do a QK comparison, up by X to be X, up by X to be, again, 4, and down by X to not really be a significant change, be pretty much 3. 1.8 times 10 to the negative 5th equals X times 4 over 3. 1.8 times 10 to the negative 5th times 3, and then divide by the 4, and I get that X equals 1.35 times 10 to the negative 5th, and the pH equals negative log of that, which is 4.87. So again, a moment ago we did this with 4 and 3 without adding anything in, and we had a pH for that solution equal to 4.62. We add a whole mole of this base in, and it only raises that to 4.87. So the pH now simply just goes up to 4.87. Again, buffer solutions can resist small amounts of additional strong acid, strong base, etc., with only small changes in pH. Alright, the next I'm going to work with here, this is a base, CH3NH2. We have a Kb of 4.38 times 10 to the negative 4. Because it's a base, in order to show production of hydroxide ion, we're going to put plus H2O. Again, a liquid. Still got to write it in order to get our products, where we get CH3NH3 ion and OH minus. And again, I'll go ahead and give you some concentrations here. Let's make this one, we'll kind of stay with what we did in the last, 4 molar. And now if we want to add this in, maybe we would do a chloride of this or some salt of this that would be aqueous. So we make it 3 molar in terms of the concentration there. If I want to find my pH ultimately, 0 here, so up by x to be x, up by x to be essentially 3, down by x to be essentially 4, equals 3 times x over 4. And now I'm ready to solve. 4.38 times 10 to the negative 4th times 4, divide by 3, and I get x is 5.84 times 10 to the negative 4, and then negative log of that value. I get a pOH of 3.23. Subtract that from 14 at 25 Celsius, of course, and we get 10.77. pH of 10.77. A couple things here. If these two were the same value, let's make it 4 molar and 4 molar, then not only would the plus x and the minus x that we're ignoring cancel out, but also the numbers would, so x would be Kb, or we would say pOH is pKb when these two concentrations initially are the same. All right, so what happens when we disturb this? You know, maybe we add in, just like we did a moment ago, some HCl. So if I add in 1 mole in that liter container, assuming no volume change, 1 mole of HCl, again, the first thing I'm going to do is I've got to find the reaction. Well, HCl is an acid, so it's going to react with the base. So I'm going to start by writing CH3NH2 plus HCl, single arrow. H is going to be donated to that, CH3NH3 plus, and Cl minus. So we had a 4 molar concentration here and a 3 here, and we added 1 mole of HCl in. HCl is limiting. Therefore, the CH3NH2 decreases to 3, and the conjugate acid increases to 4. And now, in order to solve that, I go to CH3NH2, back to my equilibrium now that I've done the stoichiometry, got my values, plus H2O, now equilibrium, CH3NH3 plus OH minus, and the values here are 3 water, 4 and none. So we get up by x to be x, up by x to be 4, down by x to be 3. And now I'm ready to set those equal in my expression and solve. So 4.38 times 10 to the negative 4th. And on the bottom of that expression, we're going to have times, let's see, 3. So multiply both sides by 3. And then divide by 4. And negative log of that answer. I get a pOH of 3.48. And I get a pH of 10.51. pH equals 10.51. So again, notice I added in a mole of HCl, and yeah, it became, acidic, a little more acidic, but not a major change. And again, that's what buffer solutions do. All right, so back to that original equilibrium expression that we had. We got 4 molar in our CH3NH2, our methylamine, 3 molar with the ion, CH3NH3 plus, and now we're going to add in 1 mole of NaOH into that liter container. Again, assume no change in volume, so we don't have to worry about recalculating any concentrations at this point. And now I'm ready to go through and do the stoichiometry. So this is a base, so I've got to identify. We got our weak base over here, and then the conjugate acid. So this is going to react with the conjugate acid. So CH3NH3 plus really just the OH minus. The sodium ion is a spectator ion in this. You can write it in or leave it out either way. I'm going to go ahead and leave it out in my stoichiometry here, and we're going to donate an H, because that's what acids do, to that OH to give us HOH and CH3NH2. So I had let's rewind, let's try that again, 3 molar here, and I had a 4 molar concentration there, and I added 1 mole per liter, no volume change, of the sodium hydroxide. My limiting reactant, 1-to-1 ratio, is the sodium hydroxide, showing that it's limiting. 2 molar with the CH3NH3+, and then this one's going to go up by 1, getting ahead of myself there, to a total of 5 molar. After I've done the stoichiometry, now I'm ready to go back to that expression, CH3NH2 plus H2O, CH3NH3 plus OH minus. And now we got some new values to plug in. I got 5 molar here, 2 molar here, none, up by x to be x, up by x to be 2 plus x, close enough to 2, down by x, 5 minus x, close enough to 5. And now I'm ready for the Kb value, 4.38 times 10 to the negative 4 equals 2 times x over 5. And ready to solve 4.38 times 10 to the negative 4 times 5, and then divide by 2, and I get an x value of 0.00109, negative log of that value. I get a POH, again, because this is an OH here, of 2.96. Subtract that from 14, and I get 11.04 as my pH. Now again, the original mixture had a pH of, I believe it was 10.77. So I added in a base, so yeah, we expect it to go up, but not really all that much when we add in that sodium hydroxide.